Welcome to the next lecture in electric circuit analysis. In this lecture, we will focus our discussion on frequency response analysis. So the introduction goes like this. We have been discussing the sinusoidal circuit analysis in the previous few lectures, where we concentrated our discussion to find the voltages and currents in a circuit with constant frequency source. So we have seen that when the frequency is constant, how we can determine the voltage and the currents in a circuit under the sinusoidal condition. So that is known as the sinusoidal circuit analysis. When we keep the amplitude of the sinusoid source remains constant and we vary the frequency now, then it is known as the circuit frequency response. So the same sinusoid circuit analysis with the varying frequency we say to be the circuit frequency response. Only the amplitude of the sinusoid is constant. So the frequency response is defined as the complete description of the sinusoidal steady state behavior of a circuit as a function of frequency. So when the frequency is varying, how the steady state behavior of a circuit is obtained, that is known as the frequency response. There are several applications like in communication networks and the control systems where the frequency response computation of the system will be required. One special example which required the frequency response is electric filters, which block out or eliminate the signals with unwanted frequency. So whatever the frequency is not required, that will be eliminated, and whatever the frequency is required, that will be passed for the desired frequency range. So that will require the concept of the frequency response analysis. So filters are basically used in radios, televisions and telephone systems to separate one broadcast frequency from another. So there are a number of applications where the frequency response of the system will be required. We have studied the transfer function introduction in the previous lecture. We will focus our discussion on the frequency response analysis using the transfer function representation. So we have seen that for any linear network, the transfer function given by h of omega, where omega is the frequency. Now if the input is given as x of omega and the output is measured as y of omega, then the transfer function h of omega is the ratio of the output to the input quantity. Now from the input side, it is a two-port network and the output side is also a two-port network. We can measure various quantities like voltage, current, impedance at different parts of the network. So we have seen that the transfer function can be the representation of impedance, admittance, voltage gain or current gain. The transfer function h of omega is basically a complex quantity. Complex quantity means that it will have an amplitude as well as the angle. So h of omega, which is the complex quantity, will have amplitude m of omega, which is the magnitude of h of omega, and it will have an angle which is phi of omega given by tan inverse of the imaginary part of h of omega by the real part of h of omega. So the imaginary part by the real part, when we take the tan inverse, we get the phase, and this is varied with respect to frequency. So the frequency will be varying in the particular system. Now we can plot the magnitude as well as the phase with respect to the frequency. It means when omega, which is the frequency, is varying, we can measure the magnitude as well as the phase with respect to frequency. That is known as the frequency response analysis. How do we determine the frequency response from transfer function? Let us take one example where we have an RC network. The input voltage Vs of t and the output voltage is across the capacitor C. Now we can convert the capacitance C into the capacitive reactance, which is Xc is equal to 1 by j omega c. Now, taking the Laplace transform of the input Vs of t, we'll get Vs, and the Laplace transform of the output, we get V0. We have to obtain the transfer function V0 by Vs and its frequency response with the given input signal in the time domain as Vs is equal to Vm cos of omega t. So the transfer function, which is the ratio of the output quantity by input quantity, if we determine in terms of the parameters of the circuit, we will get the capacitive reactance 1 by j omega c divided by R plus 1 by j omega c from the voltage division rule, and we can obtain the transfer function as 1 by 1 plus j omega RC. So we can note that this is a complex quantity having the real part and the imaginary part. So we can separately obtain the magnitude of the transfer function and the phase of the transfer function. So magnitude is nothing but the real part square plus the imaginary part square. So that will give you the magnitude of the transfer function. The phase is the tan inverse of the imaginary part by the real part. We can say that omega naught is basically 1 by RC representation in this network. Now we have to obtain the frequency response, which is how the magnitude is varying with respect to frequency and how the phase is varying with respect to frequency. So once we have obtained the magnitude and phase expressions of the transfer function, we can create one table where we can find the ratio of omega by omega naught for the different discrete values of 0, 1, 2 and 3, and the corresponding the magnitude of the transfer function and the phase of the transfer function. We can still obtain the values for other values like 10, hertz, 20, 100 and infinity. So for varying this ratio of omega by omega naught, we can measure the magnitude as well as the phase and plot it, that is known as the frequency response. So when we plot the frequency response, on the x-axis we will have the frequency, which is denoted by omega, and on the y-axis we will have the amplitude given by h. So this is known as the magnitude plot. If I want to plot the phase, I will have the omega on the x-axis, that is the variation of the frequency, and the phase phi on the y-axis. Since we have the negative direction, so we are going in the negative y-axis. So all these values of h with respect to the frequency we are plotting to get the magnitude plot. We can say that omega naught is equal to 1 by RC, which will give you the value of 0.707, that is 70.7% of the net maximum value. The phase representation, which is the plot of the frequency with respect to the phase values. The phase values is in degrees. So we have on the origin 0 degree, then we have minus 45, and then we have minus 90 degree. So we are plotting the phase with respect to frequency. So these two plots are known as the frequency response plot, and these plot we have obtained from the transfer function. There is still some difficulty in obtaining the frequency response from the transfer function. So we will go by one different method, which is known as the Bode method, or known as the Bode plots having the magnitude and the frequency. This we are going to discuss in detail in the next lecture. For understanding the basic of the Bode plot, we are going to take some introductory concept known. First topic is what is the decibel scale. Generally, we see that in communication system, the gain of any system is measured in terms of bell. So this is given after the name of the scientist Alexander Graham Bell. And then the bell is defined as the ratio of the two levels of power or power gain, and the number of bells is given by G, which is the logarithmic ratio of P2 by P1, where P2 and P1 are the two different ratio level of the power. Now, The smaller unit, when we take one unit that is bell, we have one more unit that is known as the decibel. So decibel provide us the unit of less magnitude as compared to bell, and it is 1 by 10th of a bell, and generally we prefer decibel over the bell. So the GdB, that is, we measure the gain of the system in dB, that is the decibel, is equal to 1 by 10th of this value. So when we divide this with 10, we'll get 10 log 10 P2 by P1. So when we divide these values with 10, we get 10 log 10 P2 by P1. Or rather, we can say that decibel, we can multiply this with 10. Now, if under the special cases, if we see that if P1 is equal to P2, what will happen? If the two powers are equal, the log of 1 will be 0. In that case, GdB will be equal to 0 dB. Under the case that P1 is equal to twice the value of P2, then GdB will be 3 dB, because we will have log of half. Now, if we have the P1, which is 0.5 times the P2, then GdB will be minus 3 dB. So these values will be important to understand why we have gone to the decibel scale and why we have taken the logarithmic as the important part in determining the frequency response. So the logarithmics are greatly used because we see that when we have obtained the reciprocal of a quantity, so we can see that here we have taken the twice and here we have taken the half, which is the reciprocal, we are simply getting the negative logarithmic of that quantity. So here we have plus 3 dB and here we have minus 3 dB. So that is only the negative of the logarithmic of that quantity. So that is the advantage of taking the logarithmic in our computation. Now let us take one network where the input is applied having V1 and I1 as the voltage and the current, so the input power is given by P1. On the other hand, the output side we have P2 and the current I2. So V2 and I2 as the voltage and the current, so the power will be P2. So when we obtain the decibel gain GdB, that is 10 log 10 P2 by P1, we can write the power P2 as V2 square by R2, and P1 power we can write as V1 square by R1. So this is basically the division, but since logarithmic are involved, we can convert that as the addition of the two powers. So to gain we can obtain using this expression, that is the expression involving the logarithm. So GdB we are getting 10 log 10 V2 by V1 minus 10 log 10 R2 by R1. Now let us take one special case where R1 and R2 are equal. In that case, we say that this value will be equal to 0 because log 1 will be 0 and GdB will be 20 log 10 V2 by V1. If the same computation we are doing not from the voltage side but from the current side, that is P1 is equal to I1 square R1 and P2 is equal to I2 square R2, then GdB is equal to 20 log 10 I2 by I1. So here the expression is the ratio of the voltage, here the expression is the ratio of the current. So the gain that we are obtaining for the RC network GdB is equal to 20 log 10 the output by input, that is V2 by V1, or it is I2 by I1. Now we have derived these expressions of the gain, which is the logarithmic of the quantities. So we will make some important conclusion of the frequency response and the GdB that we have obtained. So the important points that we have to note here is that when we are talking about the power expression, then 10 log 10 is used, while when we talk about the voltage expression or the current expression, then we are using 20 log 10. So that is a special difference between the power and the voltage and the current. This is due to the square relationship that is existing between the power, voltage and the current. So P equal to V square by R and equal to I square by R. So that is the reason when we have 10 in the expression of power but 20 we have in the expression of the voltage or the current. Next, the dB value is the logarithmic measurement of the ratio of one variable to another of the same type. So when we say the dB measurement, we say that the ratio are of the same variable, either it is voltage, current or the power. Therefore, it is applies to transfer function, because transfer function also we are trying to determine the ratio of the two quantities. So dB values in logarithmic will be the ratio of the two variable of the same type. Third, if we talk, only voltage and current magnitudes are considered here. When we talk about these expressions, we have taken the magnitude only. The negative sign that are involved and the angle that are involved will be handled independently. So that is nothing to do with the magnitude values. So these are basically the magnitude values that we have considered. So this lecture is basically the foundation lecture of the frequency response, where we have discussed how the transfer function is basically used to compute the frequency response of the network. And in the next lecture, we will focus our discussion on the Bode plots. So we will discuss in detail how the magnitude and phase of any system is obtained using the concept of Bode. So thank you for now.